Okay, hi, this is the intro, though I'm doing it at the very end. It's really late at night. It's after midnight right now for me. So you watching this lovely half an hour video will kind of give you the opportunity to join me throughout my journey, throughout the course of the day, interacting with some new technology. You get to meet my cat, you watch as I discover messing with color balance. It's very exciting. So be aware, technology is, in the works. Please give me feedback. You get credit, you absolutely get credit for attendance if you give me comments in the discussions about which formats worked best for you. This is the outline. We're talking about merodiploids because that's a weird concept. I'm going to give you some basic operon anatomy and talk about cis versus trans and allosteric and all of that stuff. We'll go through that first handout activity. I'm not going over the PEQs because the contents of this video should give you the information for the PEQs kind of in order of the PEQs, so go through them. The only thing that I don't directly address, I addressed the arabinose thing, so that's cool. I'm going to go explicitly directly into tryptophan attenuation because, oh my god, that's complicated. Oh my god. And the take you have is like the 5th take. I'm so tired by the end of it because it took me forever to remember all the nitty-gritty and figure it out. So it's going to take you forever. I'm here for you. The internet is also here for you, and I highly recommend all of the YouTube videos in the world. And then we're going to talk about the various repressors at the very end. I'm not going into detail about lac operon and arabinose operons. There are videos for that. I've included them in the handout. Watch those if you are struggling with lactose and arabinose. You need to understand lactose inside out and backwards. You do not, just the basics of arabinose will do for you. But it's really important that you understand lactose, that you know what all the letters mean. That's important. Okay, I was sick for the past week. That's why we're running late. I am going to send out a extra handout of answers to frequently asked questions and associated YouTube videos that might be helpful. I will start grading vocab projects now. Well, not now, I'm going to go to bed now, but tomorrow I will be vocab projecting, and so you'll start actually getting feedback from that. Sorry it's been taking so long. Everything's crazy. You know everything's crazy. Okay, you're wonderful. Stay safe. Enjoy the video. Here, have noon-ish Abby talking excitedly about merodiploids while messing with color balance. All right. Merodiploid. Mero means partial. There is no common use word that starts with mero. I couldn't find it, but it is right next to the word mermaid in the dictionary. They do not share an origin. However, mero means partial, and a mermaid is half of a maid. I mean, it's also half of a fish, and mer refers to marine, but it's a nice way to memorize it. So, merodiploid, mermaid, half of a maid. I don't know, man. Diploid means 2 sets of genes. We are familiar with the word diploid. So, a merodiploid only has 2 sets of DNA for some of its genes, not all of its genes. This is how you make a merodiploid. We start with a bacteria. This bacteria has some chromosomal DNA, and it has an F factor. Our F factor has an SI region, and so does this DNA. But it has a bunch of SI regions, as we've talked about in the past. It also has a bunch of letters. Let me draw some letters in. A, B, C, D, E, and F. See, it's funny because it's an F factor. I'm clever. Sure. Can you guys see that? Is that a little dim? I'll mess with it in post. Okay, so if these spend too much time together, they're going to interact here and become one thing, right? We've been here before. We know how this works. Eventually, it's going to be an HFR cell. And if we give it enough time, it might recombine again. Let's say it does it here. In this case, now, this is going to be E, this is going to be A. Okay, so still has all the genes. This is a functional cell. But now we've got 2 chromosomes, 2 circular DNAs that have genes that code for proteins on them. This A is important. It's going to be our operon. So this A is the operon we care about. Now we take this weird thing and we mate it with another cell. This is why I used the bad marker for this cell, because this is another cell. It's in the same species, so it has all the same genes. A, B, C, D, E. And if we mate these together, then we're going to get a marrow-diploid. This cell is a marrow-diploid, meaning that it has 2 of some of its genes, which is weird for a bacteria. Marrow-diploid. So, anatomy of an operon. This applies to both arabinose and lactose operon. So, we begin with a gene. These are the structural coding genes for enzymes and things. So, they're going to get transcribed into RNA and then translated into proteins. Our promoter is going to be blue. Promoter binds. So the promoter binds RNA polymerase, which will then transcribe the genes. RNA polymerase. All right, after the promoter, we're going to talk about the operator. I'm going to put the operator in green, because I have a green now. The operator is green. So the operator recruits RNA polymerase. So I'm going to add a little green part to my RNA polymerase that connects to the operator. The next thing is going to be yellow. And it is, oh right, and it's going to have little blue spots on it, and I'll show you why in a minute. Because this is the CAP binding site helps operator when bound, which is when glucose is low. However, none of that stuff works when we have, and I'm going to erase this part here, this is ideal functioning scenario. And in our ideal functioning scenario, there is a cap bound to the cap site, CAP, and it has these cyclic AMP attached to it. Now, the production of cyclic AMP is inhibited by glucose. And without cyclic AMP, the cap can't bind. And cyclic AMP is produced by an enzyme, which is coded for by a gene, which is on a different chromosome or a different operon. It's unrelated to this stuff. And the same goes for cap. Cap is a protein coded by a gene that is somewhere else. Another gene that is somewhere else, we're going to put it right here. And this gene coding for repressor. So this is the gene that codes for the repressor. It is not the repressor. It is just a gene. And those dashes mean that it could be anywhere. It could be on a completely different operon. It could be on a completely different chromosome functionally, though we are all in bacteria when talking about these operons. So this is what it looks like when there is low glucose for both arabinose and lac. Let's draw our repressor. And our repressor for both lac and arabinose. So for both these two, we have a repressor with allosteric sites. Allosteric. Allo, if we remember from alloploidy, means various. Steric means locations. So allosteric means it's in a different location or in various locations. An allosteric regulator binds to an allosteric site, which is not the binding site. So I'll show you the difference. This is supposed to be green. So while this is a repressor, it binds to the operator. So those colors match, and it can interfere with the ability of the operator and the promoter to bind RNA polymerase. Cyclic AMP is not an allosteric regulator because it binds to CAP's regulatory site. It's binding specifically to that site and interacting with CAP's ability to bind its target. So that's not an allosteric interaction. This is an allosteric interaction. Okay, so trans means that it can regulate stuff that's not directly connected to the same DNA. So a trans acting factor is something like a repressor. Regardless of where the gene is for this thing right here, regardless of where the gene is for this thing, it's still going to act on every available operator. CAP is also an example. So cis-acting things are things that have to be connected to the genes they're affecting, DNA-wise, or the DNA is there. So that's things like the promoter and the operator. All right, try a new system. So please give me feedback. The current activity is to, based on a lac operon, so we're in lac operon, we're going to figure out the expression patterns of the various merozygotes, so we know we're semi-diploid. We use plus if the enzyme is going to be synthesized, and we use minus to see if it isn't synthesized, and the situations are either lactose or no lactose. So the first one shows us what our wild type expression is, where in the absence of lactose, the gene beta-galactosidase which is Z. This is Z right here. That's this guy. It's going to be transcribed in the presence of lactose, but not in the absence of lactose. Permease is Y. That's this guy. Permease, and it's going to be also transcribed in the presence of lactose, but not in the absence of lactose. Let's talk about our first example. Our first step is to scan what's different. So on the first one, we automatically see, okay, Z is missing. We have a non-functional Z on one, but it's functional on the other. Now we have P, a promoter that's non-functional, and we have an O that's constitutively functional. Constitutive. All the time, no matter what. So with the O superscript C, we're going to have constitutive activity of the operator. And in this situation, a constitutively active O doesn't get inhibited. So that R protein produced by the I gene, the red thing that we were drawing, it cannot bind to the operator no matter how much lactose is available. O and P are both cis-acting. So you know that O and P are going to affect the genes on that plasmid, on that chromosome, but not on the other one. So based on this, take a few minutes, try to figure out what's going to happen, pause it, and then come back. Cool. So what's going to happen is we have a heterozygous Z. So for galactosidase, the only Z that's functional is attached to the cis-acting O that's constitutively active, but also a non-functional promoter. And remember, POIG, the promoter trumps the operator. So no matter how excited this operator is, it's not going to be able to recruit the RNA polymerase because the promoter isn't going to be able to successfully interact with the RNA polymerase. So neither of these two genes are going to get transcribed on this thing. So all we have is the activity of this one, and there's no Z there. So this is going to be a minus. This is going to be a minus because, see, there's no Z, and this is Z. But our permease is going to be okay. It's going to do normally, minus and plus. So this is the system. And if we keep going, let's highlight our weird things here. Here we have an S, a super repressor. I to the S means it's a super repressor. Our super repressor will always bind to an operator if available, no matter how much lactose is in the general vicinity. No matter what, our super repressor is interested. It's going to bind. Doesn't care whether or not there's lactose. And we have a constitutively active operator on the other side, but remember that the repressor is trans-acting. So it's going to interact with all the things. We also have a Y that is connected to our cis-acting, constitutively active operator, but this Y is non-functioning. So our constitutively active operator is going to be promoting this galactosidase, and it can't be suppressed no matter how excited this suppressor is. So no matter what, we're going to get Z from here. However, this super repressor is going to be repressing any operator it can stick to, and it can stick to this operator here on this side, this operator. So neither of these two genes are going to get transcribed. So we're not going to get any permease, but we're going to get constant galactosidase. So plus minus minus. Hope that made sense, because we're going to charge ahead. This one, we have normal but an inactive Z. And in this one, we have a non-functioning I. But remember, I is transacting. So because we have one functional I, the other functional I doesn't matter. It's going to be fine. And we have a non-functional Y. But both of those, so we have one functional Y and one functional Z and one functional I. So overall, this is going to look normal. So try to make sure that makes sense to you. But this is going to look totally normal. All right. Next up, we have no repressors. This promoter doesn't work, so it doesn't matter that this operon is constitutively active, operator. None of this is going to happen because we don't have a functional promoter. All we have is this side, and there's no repressor. We also have a non-functional Z. So there's going to be no galactosidase because we don't have a functional Z connected to a functional promoter. But there's always going to be a perfectly normal amount of Y because we have an operator and a promoter attached to Y. So we're going to have no galactosidase, and we're always going to have permease. And last up, we have a super repressor, which is transacting. It's the only repressor we got. This one doesn't work. But because it's transacting, it is going to be always inhibiting all of our operators. So none of our promoters are going to work. Nothing's going to get transcribed. This is all minus because all of our operators are normal. Minus, minus, minus. Ta-da! So those are the answers to that one. I hope that made sense and helped all of this stuff coalesce a little bit more for you. Okay, it is evening and it is time to talk about tryptophan. Let's see if I can't get you there. Let's glare. So, tryptophan attenuation. This is the operon anatomy. I'm going to talk about this, but most of our conversation is going to be about ribosomes and in the RNA and weird physics stuff. So, tryptophan has a superstandard repressor with allosteric sites for tryptophan, where if there's a lot of tryptophan, it will just sit on the operator and inhibit and get physically in the way of the RNA polymerase from going down to the DNA. But when there is a little bit of tryptophan, but not like a huge amount of tryptophan, then there's an even more nuanced way to approach that situation. And that has to do with the RNA and this leader region and that red line there. And we're back. Now that our RNA polymerase has started making some RNA, this is our RNA, and we're in bacteria, so the ribosome is just going to jump right on that and start heading this way, and our ribosome is going to be making protein, so I'm going to zoom in real quick. Okay, this is confusing. Let's walk through it. This is just a zoom in of this fragment of RNA. So this is all RNA, and these are the codons that are in there of the RNA. This is a start codon. So our ribosome, if I can find my orange, is gonna hit this start codon. It's gonna hit it at about the time that RNA polymerase is here. 1 and 2 are then going to create a little hairpin, because 1 and 2 are complementary, those two regions. And that's going to cause the ribosome to pause, regardless of whether or not there's a lot of tryptophan. It's going to allow RNA polymerase to continue on to this area here. Once 3 has been transcribed, 2 and 3 are going to pair, 1 is freed up. And this is when it matters whether or not there is tryptophan available. If there's plenty of tryptophan, then the ribosome is going to head on forward, and it's going to go straight through these 2 codons, because these 2 codons code for 2 tryptophans. Once 1 is freed up, the ribosome is gonna be fine finding those tryptophan amino acids because there's plenty in this scenario. However, immediately after those is a stop codon. So the ribosome is gonna get stuck on this stop codon. And because it's right here, it's gonna prevent 2 and 3, it's gonna force 2 and 3 to disconnect. So ribosome, being able to translate 1 easily, undoes that 2 and 3 pairing. The RNA polymerase is going to keep going and translate 4. 2 and 3 are not paired because ribosome is blocking 2. It's on 2, essentially. So 3 and 4 are going to pair, and they're going to create a hairpin loop. 3 and 4 are a hairpin loop now. And right after 4 is a U line. And this hairpin loop followed by a lot of U's, we've seen this before. It means that it's going to stop transcription. So the ribosome has hit a stop codon. This is going to be a protein fragment. It's going to get thrown away. However, the RNA polymerase has now hit this termination sequence with a hairpin loop and a bunch of U's, which is going to cause the RNA to come away from the DNA, and it's going to stop transcription. So that's the scenario with a lot of tryptophan. Now, let's go through less tryptophan. If there's no tryptophan available, just so little tryptophan, then when our ribosome gets to 1, and we remember it was at 1 as soon as 1 and 2 were freed up because the RNA polymerase had just done 3. So here, our ribosome is on 1, but it's going to stall. It's going to sit there for a little while. And because it's stalling, 2 and 3 are going to be paired together when 4 is transcribed. So our hairpin loop in this scenario, because the ribosome is on 1 and it's not on 2, that hairpin loop is going to be here, which cancels out this sequence. Those U's are going to be fine. They're going to get transcribed. RNA polymerase is going to keep going. So the ribosome sitting on 1, maybe eventually it'll find some tryptophans, but if it does after the RNA polymerase has passed these U's, that's fine, it doesn't matter. This ribosome is going to keep going, it's going to hit this stop codon. This is going to be a protein fragment that goes away. Even with almost no tryptophan, we're still going to have that extra protein fragment. However, after this UU sequence is another start codon up here, AUG. So after this UUU, RNA polymerase is going to transcribe that and then transcribe another start codon and keep going. And another ribosome is going to jump on this end once this falls off, and it's going to find that new start codon. So, to recap, with tryptophan, lots of tryptophan available, there's going to be one protein product from this operon. It's going to be, well, with lots of tryptophan, it's going to be inhibited because of this. With enough tryptophan, this is going to produce a single little fragment, but it's not going to transcribe the whole gene process. With almost no tryptophan, it's going to produce 2 gene products. This trash piece and all of these genes that will result in proteins that are enzymes necessary for making more tryptophan. One last thing, I'd like to talk about the repressors and their effector molecules for the three operons that we talked about, lac, trip, and arabinose. Lactose, tryptophan, and arabinose. So all of them have allosterically interacting repressors with their allosteric effector molecules, and they all affect the output of their operons in different ways and directions. So let's put them all on a board together to keep it straight. So, our lac operon has a repressor which binds lactose. So its repression activity is blocked by lactose. It can't bind to the operator when lactose is bound. So repressor plus lactose equals no interaction with the operator and transcription. Up lactose leads to up transcription is the net result of this. So for the trip operon, we have the opposite situation. We have a repressor activated by tryptophan. That means that it can only bind to the operator when it is also bound to tryptophan. Tryptophan allows the interaction with the operator, thus, up tryptophan equals down transcription. It's the opposite. Arabinose is a weirder situation because it has the RC thing, which can be either a repressor or an activator. So RC bound to arabinose is an activator. RC without arabinose is a repressor. So when we smoosh that weirdness together and simplify it down, we just get up arabinose equals up transcription. Ta-da! Clean cut.